So we have, go back to the geometry. Okay, well, so let's look at 2 dimensions. Here's X, here's a Y-axis, and let's say that I have this vector here, which is 3, 1. This is the format X, Y, right? So this one is, well, let me extend this x-axis out here. So this is 3, 1. And let's say that we also have this one, which is 2, 1, 2, 3, 2, 4. Okay. Well, and you can see that there's a parallelogram. If I go over 2 and up 1, 2, 3, 4, that's the same as going 1, 1, 2, 3. So if I make this parallelogram here, like that, and let me move this 3, 1, so it's not quite in here. 3, 1. It's this vector here. Well, this area here is going to, if I make the matrix, where this one here is 3, 1, and this one here is 2, 4, then this matrix, the determinant of this matrix here equals area A. That's the result. That now there's 2 things going on here. You know, if I was to do it in the other order, if I was to do 2, 4 and 3, 1, I get a negative. That's going to change the sign of the determinant. So it'll be the same area, but it'll be a minus sign. Well, that corresponds to what's called a right-hand rule. So it turns out that the right-hand rule corresponds, if I take my right hand and put it sort of so it's on this shape here, like this, like that, then it's going to be so that this first vector, so that this vector rotates into this one in a, you go from this way, this one to this one in a counterclockwise direction. So if you're sweeping from here to here, that's a counterclockwise direction, then this is going to be a positive number. It'll actually be the area. Now, we can see what this is according to the formula is, using the formula, say it's going to be 3 times 4 minus 2 times 1, which equals 12 minus 2 is 10. The claim is this is 10, right? Well, we could try to verify that, maybe with a little more precision. Doesn't look very precise. But we want to go, let me see, we need it a little bit more precise than that. Actually, we want to go over, say, 1, 2, 3, 1, and over 1, 2, 1, 2, 3, 4, and then we go over 1, 2, 1, 2, 3, 4. Oh, let's see. Okay, that was a bad idea to do it with dots. Okay, so we want to do okay, now let's look at this shape here. Okay, and then we can divide this up into some other small shapes, right? And we can see that the big area here, we can see that area A in blue is going to be area A square, right, minus the orange. Oh, no wonder that was doing weird stuff. Okay, minus A for the square, A for the whole square here. If I take this entire, the area of the blue here is minus orange areas equals the blue A. Because I can see that this whole, let's do this calculation explicitly. We can say, well, this is 1, 2, 3, 4, 5. So this area here is 5 times 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So it's 5. This big area is 5 times 5. So we subtract off. We can see there's a 2 here and a 2 here. 2 times 2. And then there's 2 of these small triangles here that are, there's 2 of them. And each area of the triangle is 1/2 the base times the height. That's 1/2 3 times 1. That's this area and this area. Then there's this one. There's this one and this one, which is 2 times 1/2, 1, 2, 3, 1, 2, 3, 4 times 2. So this is going to be 25 minus 4 minus the 2 and the 1/2 cancel, minus 3 minus the 2 and the 1/2 cancel. 2 times 4 is 8, which should equal 25 minus 15, right? 8 plus 4 is 12 plus 3 is 15, which equals 10. So now if I did, interestingly, if I put in these coordinates as like x1, y1, and this one is x2, y2, and I did this same calculation out, there'd be lots of cancellations too, and I'd be left with x1 times y2 minus x2 times y1. So it would be the same formula, and it would work. So somehow the determinant formula is like the area, but with all this extra stuff collapsed. So it doesn't look like an area. Okay, well that's in 2 dimensions. Now it works the same way in 3 dimensions. If I have in space, like V1, V2, and say V3. So this forms some kind of cube. It's actually a parallel, it's actually like some kind of, it's going to be a mesh drawing, which like you can see, it's like, it's going to be some kind of parallel pipette or some kind of like that. But it's going to have a volume here. So if this was like 1, 2, 3, and this second one was like 4, 5, 6, and this one was 7, 8, 9, then the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9 will equal the volume that's enclosed by the parallel pipette. Okay. Well, you can imagine, although you can't visualize, that if you had 4 vectors in a 4-dimensional space, that it's going to have some kind of hypervolume. It's going to be like, and you can sort of, you're going to have the same idea that there's going to have some geometric hypervolume that's going to determine what's going on. But that doesn't, that's hard to visualize, but you can see in 3 dimensions, this volume actually, has a meaning. And so the idea here is that if you reverse the order of the things, it's like this is a right-handed coordinate system. So if V1 goes counterclockwise into V2, and then the V2, V3 plane, V2 goes into V3 counterclockwise, and then the V3 from this goes counterclockwise. Then you have what's called a right-handed coordinate system, and there's like right-handed and left-handed coordinate systems. So if you that's actually changes what's called the pair. That actually has a meaning in terms of physics. Sometimes in terms of physical things, that you can't move around the left and right-handed coordinate system into each other. It's sort of like you can't sort of lay these on top. You have to make them opposite, like your hands. So your hands are sort of like left and right, and they don't superimpose on one another. You can't make them. Well, you have to sort of like flip one over. Okay, so the sign has a meaning here in terms of the relative orientations of the axes. And in 4 dimensions, you have the same thing. If V1 goes into V2, and V2 goes into V3, and V3 goes into V4, and V4 goes into V1, and in each plane that's counterclockwise, you get sort of a particular orientation of the volume, and you can have other orientations. Okay, well, that sign gives you a geometric interpretation of the volume and the sign, and this is actually has all kinds of connections in Calculus 3 and other stuff. So we're only interested in the volumes of this stuff. Now, what's interesting in this regard is how you deal with what the geometric form of row operations is. So if I start with a box like this, where this was like 1, 0, 0, 1, well, that we determined at 1, 0, 0, 1. So if I take that to be 1, we think of this as a unit 1 matrix, right? Well, if we do a row operation on this one, if we do a row, like if we do, let's say we do 2 row 1 plus row 2 on this matrix. What does this go to? 1, 0, 0, 1 goes to 2, it goes to 1, 0, 2, 1. Well, what is this geometry of this one? This is, the first matrix is, goes over 1, which I'm 3 over, and then it goes up, let's see, 1, 2, 3, 4, 5, 6. Okay, but the second one stays the same, 0, 1. Okay, so what I have is this is the transform first vector, and this is the second one. Okay, so then if I go, let's see, I think it goes the parallel. So basically, this row operation shears this shape here into this shape here. Well, those have the same area. There's something about this one. It's still equal to the base times the height. So the height is this 3 here, and the base is still the 3, and the height is still, well, I'm doing it to make it larger. This is like 1 and 1. So it's still the same, so it still has the same area. So what a row operation does is it shears the box horizontally, but doesn't change its volume. Now, if I multiply, let's say if I multiply, I do 2 row 2. Well, that's going to produce the matrix 0, 1, 0, 2, which if I look geometrically, that's going to be 1, 0, but then 0, 2. So that doubled the size of the box. So this one, that's why the area doubled, so the determinant doubles. So that's what this one does. And the other one, like if I do row 1 to row 2, that's going to produce this one, right? It swaps row 1 and 2. Well, what does this one look like? Well, the first vector is instead of 1, 0, it's 0, 1, right? And the second vector is 1, 0. So what's happening then is we're going the opposite. You know, if we do this one here, this is like the first one is 0, 1, then 1, 0. So it's the opposite way, right? So basically, this would be the same area, but with the axes interchanged. This would be like the x-axis and the y-axis. And so the sign tells you about the orientation, sort of like, and sometimes in physics it's used for the surfaces, like sort of the upper surface or the bottom surface. So you can use the sign for all kinds of reasons. If you have like a surface of a sphere, then you can think, well, the arrow pointing outwards and the arrow pointing inwards tell you the inside and the outside of the sphere. And so that can be related to a determinant and a sign of determinant. Okay, so that gives you sort of a geometric interpretation of row operations and determinants as areas and volumes. And anyway, so sometimes there's a relation between what we call cross products and determinants, and cross products are used in physics to do some kind of magnetism stuff. And sometimes the forces between particles have this same sort of shearing quantity that only depends on like the cosine of some distance angle between them or something. So you end up with sort of, if there's like a magnetic field and a thing moving here, it won't matter like sometime. Anyway, there's connections with all this stuff there, but we're not going to explore that. Okay, well that's basically